So we have Yevgeny Kovchikov from Oregon State will tell us about random self-similar trees, dynamical pruning, and applications to inviscid Burger's equations.
Thank you. So first of all, I want to mention that this is a joint work with Ilya Zalepin of University of Nevada, with whom we've been collaborating since maybe 2008 or 2009, I don't remember. And then recently, Maxim Arnold joined us he's from University of Texas at Dallas, and he is an expert on Burger's equations. So a lot of things that I'll tell you about Burger's here, I learned from him. So I'll start with terminology that will be used. Unfortunately, I couldn't avoid it. So first of all, the space that we are dealing with, I'll denote by L plane. So it's a space of finite, unlabeled, rooted, reduced binary trees with edge lengths and planar embedding. Okay, a bit long. Now the reduced part is here. So series reduction. So we consider as vertices only the junctions and the leaves and the root, but we do not have vertices of degree 2 because we just make them middle of the edge. So and they're reduced in that sense. Binary now they're embedded planary and then they're rooted. So that means that we have left-right orientation and up to down, towards the root, away from the root, up. Now each tree has a root, so the empty tree, the smallest tree we have, will be denoted by 5, and it will consist of only the root. Here I draw it. Now we have edge lengths, so we have the distance between points on the tree. So essentially we are talking about metric space with a fixed distance function. Now the two functions of trees that we will use quite intensively will be the length of the tree. So the length of the tree will be the sum of the lengths of all edges. And then the height of the tree is the distance, the furthest distance among the leaves to the root. So the biggest distance between a leaf and a root. Okay. So first of all, one more notation. Delta xt, so take any point x on the tree, and delta xt will consist of all the points on the tree. So it's a subtree above x, where you will make x into the new root. Now, with such, we have a partial ordering. So when do we say that T1 is smaller or equals than T2? If there exists an isometry from T1 to T2. So isometry would be a function from T1 to T2, so that the image of T1 will be included into delta f of rho 1 T2. So essentially, this condition would preserve the orientation, and then the distances between points after the mapping will also be preserved. So essentially, you're embedding T1 into T2. Maybe you would switch left or right sometimes, but just to say what tree is bigger than other. Okay.
It's not onto.
What?
Is it onto your map?
It's not onto. Yeah. So essentially, it says that we can carve out a tree T1 out of T2. And so that the orientation is preserved. Up is up.
Injection, I see.
Yeah. So that makes partial order between the trees, and we'll need that partial order in order to define pruning. So what would be the generalized, what we call generalized dynamical pruning, because it generalizes lots of various prunings that are described and studied in the literature. Well, that would be the map from L plane to R plus, such that it will be monotone, non-decreasing with respect to that partial ordering. Okay, so in the next few slides we'll give examples of functions like this. So once you have a function like this, then you can define a mapping that is parameterized by time t, such that it maps trees in L plane into trees in L plane in the following way. It will definitely leave the root alone, right? So as any mapping. What would it do next? It would look at every point x on the tree. It will look at delta xt, the tree above x, and if that non-decreasing monotone function phi that we've selected of delta xt is bigger or equal than t, then this point stays. But if it's smaller, then this whole tree is erased, including that point x. So the monotonicity part guarantees the following, that S sub t is going to be itself a tree. So essentially we erase parts of the tree from top to down according to that function phi. And also we know that if S is bigger or equal than t, then we erase more of the tree from top to bottom. So what's left is going to be at least small or equal. Okay? So this gives us a universal way of eroding the tree from leaves down. All right. So here's some known and novel examples. So say let's take that function phi to be the tree height. Well, tree height is definitely an increasing function, right? If you can embed a tree T1 into T2, then definitely the height of T2 is going to be bigger or equal than that of T1. And moreover, I mean, because we did it so that the orientation up and down is preserved, right? We're not talking about the diameter or anything. Now, if we pick phi to be that height, actually the generalized pruning introduced on the previous slide coincides with the tree erasure procedure described by Navu in his 1986 paper. And by the way, relevant to what I'm going to be talking about, there he establishes an invariance of critical and subcritical binary Galton-Watson processes with IED exponential edge lengths with respect to that tree erasure. So tree erasure is probably the most natural way of pruning. Essentially, you set fire on every leaf, and then it burns with the same speed down towards the root. Okay. What is also notorious about it is that, of course, the semigroup property it satisfies. If I freeze, if I put down the fire and then restart again, then I would have the semigroup property that it just continue. Yes.
Just to clarify, when you say invariance, this is like quasi-invariance, because sometimes the tree will disappear, so you condition on.
Yeah. Quasi-invariance, you do condition on survival of the tree. Yeah.
Okay.
Good. Now, another
people would worry, how can you make a tree smaller and still have it in
Yeah, absolutely. So we think about, you may think about a forest, and you raise you prune every tree and just count the survivals and the statistics of, yeah, absolutely. Now, this is the pruning I'm going to be concentrating on.
Because I think this is a key point. So is this clear what this invariance means? Sorry, please.
Yeah, thank you. Actually, I should have paused and asked for questions. Yeah.
I'm sorry, could you go back to the regime in which it's invariant?
We're gonna. There's a special slide about invariance.
Okay, great.
So I just mentioned that it's kind of like a sneak peek.
Okay,
Okay.
thank you.
I'm sorry for organizing slides this way. I mean, so the one that we're going to concentrate as an application today is going to be the length. So what is the length? The length is again is the sum of all edge lengths in a tree, right? So it's very easy to see that the pruning operator that we create with this function is not going to be a semigroup. And I'll draw a picture. I meant to draw it before, but maybe somehow I forgot drawing all other pictures. So, so imagine a tree, and you consider one of the points x which are on the junction. So it's one of the points that we consider vertices here. Now imagine that you calculate the length of the left branch, right? Let it be L, okay? And the length of the right branch to be R, but the length of delta xt, or the tree above x, includes left and right? So it's going to be L plus R. So what could happen? It could, because we are erasing trees, subtrees according to their length, right? If the length is less than t, then it's erased. So if you look at time t, which is bigger than max of L and R, and smaller than L plus R, right? Then what happened? What happened is that we erased all the points here on the left, all the points here on the right, and then we pause for that much time. And if we stop the process and then start the erasure, then we will not remember that we have to wait more time till we renew. So that you will not have the semigroup property, but you could of course fix it by creating like a sticky point here, which kind of counts time. And that would be exactly a massive point, a sticky point in solving Burger's equation. So you can make it a semigroup if you introduce heavy points, like timers, essentially. Okay? And so this is what our application is going to do. That's a bit later. Now, so I want to complete the picture with the third example. I mean, I thought of giving 2 examples is not sufficient, and 3 is the golden rule, I think. So third example, we spent many years studying, so it's not a waste of time, I hope. So it's called Horton pruning, and it's tightly related to Horton-Stroller ordering that originated in hydrology and computer science and many other applications, biological applications. So what is Horton pruning? Well, the picture on the next slide will explain it all. Maybe I should start with the picture on the next slide. Why not? Instead of, I mean, you made me think about in which order to present. And, yeah. So you start with a tree, and then Horton pruning does you erase all the leaves, and then one iteration, and then do what? Series reduction. So if this was t, this is r of t. You do one more, r square of t. Do one more, r cube of t. If you're down to the empty tree, you stop and count how many iterations you did. 3. So you say, okay, the Horton-Stroller order of this tree is 3. Okay? So, and that's what Horton pruning would do if you let phi of t to be the Horton order of the tree minus 1. So for every delta xt, we will therefore we'll look at the Horton order. Now, well, we need to do minus 1 because at time 0 we don't want to prune, right? And so actually, all iterations happen in integer times. And arguably, although we have that conjecture which I think we are closing on, but this would be essentially all prunings that are semigroups at integer times, at integer values.
Go back to the previous slide. I didn't understand.
Yeah.
When you go to R of t, and then
Yeah.
you do once more, so you remove.
I cross the leaves
You remove the leaves, I see, and then you.
and then do series reduction. Yeah, everything we do here is mod series reduction. Yeah, and so 3 rounds, and then why is it important for hydrological applications, for all kind of computer science applications? Well, because it builds a hierarchy on a tree. So whatever was erased on the first round is given order 1, second round order 2, third round order 3, and so on. So there is a bit of overlap in the literature because the more computer science-minded people like to call it register number. And it is instead of Horton-Stroller order, and it equals the minimum number of memory registers necessary to evaluate an arithmetic expression described by a tree T. Now, of the papers on the topic, the first theoretical paper of interest here is that of Bird, Weimar, and Wien, where they consider again critical Galton-Watson and Galton-Watson. And show some type of invariances called Tokunaga or Horton self-similarities. So now, one of curious things that one of our first observations about it when we started working on Horton prunings was to notice that if you take a level set tree, so let me just, to be logical in order, tell you what level set tree is. So you would make all the local maxima into leaves, and all the junctions will be the local minimas in the corresponding order. Okay. So if you and you can always go between level set 3 and back if you look at the Harris path. Right. So what we noticed, and what kind of our first results explaining some self-similarities or invariances which I haven't defined were based on the following: that if you take a function and look at its level set tree and then prune it, what tree would you get? You would get the tree, a level set tree of the interpolated function of local minimas. So each time you prune, it corresponds to taking local minimas. So you prune twice, you take local minimas of local minimas, and so on. And in that sense, we had a lot of fun playing with it. Now, I just want to quickly clarify what we call exponential critical binary Galton-Watson tree. Essentially, this Galton-Watson tree is in continuous time, so every edge is exponential. Yeah. So let me just be that brief about this slide. Now, something interesting that was noticed long time ago and appears in the literature is that if you take an exponential excursion, so how do you generate excursion? You would go up by an exponential flight, down, up, down, till you cross over to the negatives. And look at the level set tree. Then what you see is exactly that critical Galton-Watson tree with exponential edge lengths. So now, this being our object, we proved a small theorem about the general pruning, the generalized pruning, that's how it's called, but it will have implications. So what does it mean? So that theorem says, take any increasing function phi and the pruning operator that comes with it, and look at the tree that you obtain by randomly selecting tree T according to Galton-Watson, exponential Galton-Watson, critical Galton-Watson, critical binary Galton-Watson, so probability 1/2 for branching. And then if you prune it for time t, conditioned that after time t the tree didn't disappear, so it didn't get reduced only to the root, then it's still going to be Galton-Watson and still critical and still with exponential edge lengths, except for the exponent is different. It can be represented as L times P sub t. So this is being the new parameter, and P sub t being the probability of that exact event that we condition upon, that a tree selected according to Galton-Watson has not been erased. With obviously we want this to be positive, so given that that probability is positive, which of course we could make a weird phi function for which it would be 0. So essentially any of these prunings would take critical Galton-Watson into critical Galton-Watson, and we check the dynamics of the edge lengths. Now for the 3 examples, if phi is the total length, that would be the new rate, where I0 and I1 are modified Bessel functions. And you easily can check with this formula again the absence of semi-group property. For phi being the tree height, so for the erasure by Navier, this would be the new rate, and for Horton-Stroller, that would be just the rate. Each integer time lambda will be halved. So each integer time you prune and you get twice longer edges. All right, this is the slide you were waiting for, the invariance. So I should start with the bottom of the slide to be logical, right? So our main goal of all this study is not particular applications like in hydrology or in computer science or Berger's equation. Our main goal is finding the invariances under these prunings. So we need a measure like Galton-Watson measure that generates trees such that if we prune and condition on not the whole tree being erased, then we get the same distribution, maybe scaled. Like lengths get scaled. So essentially think about it as some kind of shift distribution, right? You raise the trees from the leaves down, and you're looking for invariances. And this is the slide you were waiting for, okay? Now, these are unrelated results, and I'm not going to go into defining those orange things. Yes, I thought of it as kind of curiosities. As I said, we started with answering some hydrological problems, and so one of those was concerning Horton-Stroller orders, that is, if you have self-similarity under pruning, meaning the merger statistics of order I into order J stays the same on average, then you would have what's called strong Horton law, which is a geometric law for the number of branches of orders. So this was an open question for in hydrological community, and that's what we found really interesting and studying. The other one was studying invariances under Horton pruning of trees created by Kingman-Coaleston, and we've shown a weak version of what's called Horton law there. But of the curiosities again, I wanted to highlight the following fact, that from Horton pruning perspective, the Kingman-Coaleston tree is only one pruning apart from the Levelset tree for IID time series. For white noise. Okay, statisticians don't like time series IID to be time series. So more like white noise. Okay, so in that sense, the trees are essentially the same, and the result hold, which was kind of curious. I mean, first we arrived to it purely by formulas, and then I realized that it was natural. Now, here's the application I announced in the title of the talk, so I have to go there and go through this application. I actually also find it very interesting. This application has to do with the pruning where a phi function was picked to be the length of the tree, right? So exactly this type of thing. So let's try it with 1D inviscid Burger's equation. The first part of the talk, where we don't go into the analysis of the trees, would work in any dimension, I should say. But here we restrict ourselves to 1D. So now let's take 0 external force. So on the right-hand side, we'll have 0. There is a standard way of introducing the potential velocity field by substituting, instead of V, negative the derivative with respect to x of psi. You plug in under additional assumptions which you can easily derive as proportionality of to the density function. But you would arrive to this Cauchy problem with some initial conditions. Okay, so essentially that's what we are solving. Okay. Now, and I copy it here with the initial condition. Now, before the first collision of particles, the Burger's dynamics is straightforward. You have the starting point, you have starting velocity, you go with that velocity. And the most interesting stuff starts with collisions. So, and in that sense, after the collision time, what you do, you modify the equation by introducing actually a small viscous term with a tiny epsilon. You know that the solution of this equation would be well defined. The Hopf-Kohl transformation given here, and in general dimension with the Laplacian, not with the it gives an integral representation of the solution for epsilon, any epsilon here. Now we obtain the solution of our equation, not to say it's a classical known problem, by letting epsilon go to 0 and looking where this solution goes. And the Lax-Alegnik variational principle implies that this will be the formula for the solution. So, so I copy that formula here. So, and then what does it mean with respect to psi 0, the initial potential? So imagine this being the initial potential psi. Now you have points here on this negative slope going left, here on this positive slope going right. Now, the quadratic term here says the following. Suppose we can inscribe a parabola so that it is tangent to the potential function on both sides. Let's look at the corresponding interval on x-axis, and let's look at the minima of that parabola also projected on x-axis. So all of this points will collide into one massive point here at time t. And t, how do you know t? Well, this is the coefficient when you inscribe the parabola. So by time t, they all will be here. So what does it mean? It means that by inscribing parabolas here, we know where the massive point originates. Then the massive points, when they absorb everything they could absorb from left and right, start moving and then colliding. So you would get a shock wave tree. Okay, so this is the shock wave trees that we're going to be pruning. Okay, and we show that the pruning dynamics will essentially correspond to the Berger's dynamics if we start placing sticky points on the tree. So as our first exercise, and that's what I'm reporting here, we take initial placement of velocities, initial placement of particles, and velocities alternating from positive one, negative one. So you alternate the particles left, right, moving initial velocity left, right, with plus or minus one velocity. So same velocity, just going left or right. You later on we'll assume that the points are placed according to Poisson point process. So that would be like one-dimensional analog of Zildovich conditions from astrophysics. So what would be the potential, initial potential then? Well, I mean, exactly like minus 1, plus 1, minus 1, plus 1. This is the slopes, right? So for this type of potentials, the shock wave tree is very easy. It's really easy to inscribe a parabola into negative 45 degree corners, right? So we do know that the massive points will originate here. Now, we model the shock wave tree as an upside down level set tree, or the level set tree of the upside down potential, however you like to see it. So what will happen here? You will have here points going left and here points going right, generating massive particle till this whole edge is eaten down, and then therefore the massive particles start moving left. Similarly, you have one originating here, and this will be the time needed for all of the points on the left and on the right to collide into the massive particle until it starts moving to the right. If you cut this corner by just making one corner like this, right, and inscribe a parabola, the minima is going to be here. It's going to correspond to the intersection of those two lines. That's where they're going to collide and move on. Okay, is this clear? I should.
Evgeny, show me your left hand.
Left hand?
Yes.
Okay.
Yes, because I had a feeling that left and right in your description were reversed relative to the standards.
Okay. You're right, actually. That's very good psychological observation. But no, but I meant the other left.
Alternative left.
Alternative left, yeah. Yeah, whatever political replications it is. So now let's see how the trees work, and how is erosion going with those trees. So imagine we started with a potential like this. I already cut the corner here. What happens with time t? Well, all the points here on the right slide towards the left. All the points here slide in, and so we get these flat planes in the potential. Same thing here. What does it correspond to the vertical? Because each each leaf has a vertical and horizontal component. Vertical is the accumulation of the massive point. The horizontal is the movement before the collision. And what you see is that beginning this vertical matches this horizontal, and this vertical matches that one. And so if in our level set tree we only interested in the vertical displacement, that's what our tree will be. And by time t, it will be eroded by on the left and on the right by the length of time 2t. So essentially, you get erosion. So this part got eroded and this part got eroded. Okay, and whatever got eroded accumulates into the mass of massive points. And so if we go, this is from our paper, so this is really like a movie. So if you go on, what happens is this edge is eaten away, left side, this left slope. So we have a plane here. What does it correspond here? To the erosion of this leaf on the right, although it's left actually. Okay. And this. An appearance of a massive point in the middle of a leaf. Okay, 5 minutes. Okay, I'm almost there. And then what happens next? Well, this slope erodes, right? So we essentially ate away the left and the right sides. And now, you may think about it as now one double massive point sitting here and waiting for the collision. That's exactly that case with the raising by lengths, where you eroded the left side, eroded the right side, but then you're waiting for before you restart moving. Okay, so that's what corresponds to this case. Would correspond to the double massive point on the leaf. And then the dynamics goes on. Once they meet, they start moving. So if we, how about I say it here and then, I mean, the slides are placed in the most logical order, as you already know. If we start with placing particles according to Poisson point process, then what are we having? We are having those exact exponential excursions for which the level set trees are going to be critical exponential Galton-Watson trees. So if we start with that initial condition, this will exactly correspond to the case in the theorem that we stated. And that is part A of this theorem saying, okay, at time t, the tree erodes and erodes so that its condition on its survival, it's going to be still critical Galton-Watson, but with the new rate. And moreover, we can actually track, so we can always draw back the potential. So if we have the eroded tree with massive points, we can always get back to the potential. So from this, we have a complete description of the potential function distribution at time t for this Zildovich kind of conditions. So here it is. So starting with exponential excursion as our potential with parameter lambda over 2 for each flight. Then the tree that we get at time t of Berger's dynamics will be the Galton-Watson with parameter lambda sub t, which is this. That was part A of that theorem. Now, what else? Next, a single or double massive point are placed at the leaf. How? Well, it's a single point with this probability and double with the corresponding probability, like 1 minus this. Okay, the complementary probability. That's what I have. So some will have double, some have single. What else? What else is each single mass at leaf is a mass m equal to 2t. No, I mean, if it's single mass, then it's always twice the time. If it's double mass, I need 1 more minute. If it's double point mass, then we have joint distribution. This is the case where when left and right side eroded, but the massive points still didn't collide. And that would be it, still expressed through these functions p sub t and L of t, which are in turn expressed through modified Bessel functions. What else? We can also place massive points in the middle of the leaves. That corresponds to the case when one of the leaves eroded, but the other one hasn't. So, so the other massive point is still growing. And that would be just geometric with the corresponding probability. Geometric, but starting with values 0, 1, 2, and etc. With the corresponding probability p sub t from the other slides. So we have some of these points. Now, what are the masses of the points that we are placing on the leaves? Well, and by the way, they could be a left one or the right one, right? It could be the right massive point already stopped growing and started moving, but the left one is moving, or vice versa. So those are with probability 1/2, of course. The masses of them have this distribution. So each of the masses has this distribution, also described through Bessel. So we give complete description of the distribution of the potential at time t. Now, okay, if we place, if we don't start with just an excursion, but start placing just points according to Poisson point process from left to right, then of course it will consist of this mini excursion. So we have the description of the dynamics of massive particles. So essentially, if you take a randomly picked massive particle, its mass will be distributed this way. If it's moving, its mass is going to be 2t. If it's still forming, its mass is going to be distributed this way. And this is a picture. So either it's on an excursion or it's still moving. Finally, I just want, this is the last slide. Oh, I'm so ignorant. Wrap up, I see. Okay. So what is related results? Our result has some similarity, although it's different. We tried to regenerate some of the known results from this one. But what was it? Say Sinai's work, 1992 work. You start with white noise. You do Berger's dynamics. At time t, it's still white noise. But these are different results, and the result of Bertoine and Giraud, and then they're of the same kind, same flavor, but they're different. Now, what are the perspectives? The perspectives, of course, we want to expand the Berger's dynamics into a larger class and higher dimensional case, because we can still inscribe paraboloids. We can still have the shockwave trees. That's what they are. Interesting thing with those invariances was the models of statistical mechanics and criticality exhibiting those. So there are some really important questions. We actually generated our own hierarchical branching process that behaves the way we wanted. Okay, I'll stop here because wrap up is wrap up. I mean, I just.
You have a question for Evgeny?
I have one.
Okay.
Have you thought at all about connections between this stuff in any way and continuum random trees?
Continued random trees. We thought. I mean, we even read some of the papers in that direction to see. You see, the problem with combinatorial stochastic processes in general is, for us, what we do is we do statistics from leaves down. So if you look at the level set tree, you can generate an infinite level set tree if you start with a Markov a random walk from left to right, because from leaves down. Now this is going to be an infinite tree that you generate from leaves down, but you'll never reach the root. And whatever combinatorial stochastic processes study is mostly from the root up in an infinite, if they build an infinite tree. For us, it's like from leaves down. And that's almost like 0-1 law. I mean, whatever our infinite tree built from leaves down is doing has nothing to do with the infinite tree built from root up. So that, yeah.
Question. I just want to make sure, because I'm not sure if I understood. You had this example, the velocity is either -1 or 1.
On the left or on the right? Okay. Yeah.
So the point is, was it just your example, or is this your assumption in your theory?
This is our assumption. I'm sorry for...
So velocities are plus or minus?
Yeah, and the points are distributed according to Poisson process. Yeah. Thank you. I mean, again, I think I went very fast. It was supposed to be Zach Gelbaum giving this talk. So I interfered, but this was my 50-minute talk. So I promised myself to talk it in 40 minutes.
Thank you, Evgeny, especially for giving this talk at such short notice.
Thank you.